Francesco?
Yes, thank you, Fernando. Can you hear me?
Yes.
Okay, so I'm not completely sure it will work if I keep my video on. So let me switch it off, and then I will start it again for the questions. So okay, so thanks a lot for the invitation to the organizers, and thank you all for being here. I hope you are doing well given the circumstances. Today I will tell you about a topic that we have been exploring more and more in recent years, which is moduli stars, and the results that I will illustrate are mainly contained in these three papers, written in collaboration with a bunch of people you all probably know as Sven, Fernando, Michele, and Francisco. Then there is also Gianpaolo, who is in Bologna, Katie Clough, who is a postdoc in Oxford, and the Basel group composed of Stefan Antush and Francesco Cefalà and Stefano Orani. Okay, the main idea comes from the fact that we have recently detected gravitational waves, and as you know, they basically are a unique probe of the early universe. In particular, especially because, as you know, the early universe before photon decoupling is opaque to light. And especially, we might be able to explore the first second of the universe, so pre-BBN physics, using gravitational waves. Given that as we go back in time, the temperature of the universe grows, gravitational waves might allow us to probe very high energies or temperatures. As you see, with LIGO, one can even probe up to 10 to the 10 GeV. This is taken from a review by Chiara Caprini and Dani Figueroa on gravitational waves of cosmological origin. With the gravitational waves, we might have a chance to climb over the wall, which is represented by the CMB, and explore the physics of the early universe. And there are many phenomena that in principle could give rise to gravitational wave production in the early universe. But in this talk, I will mainly focus on preheating, so non-perturbative dynamics, and formation of exotic compact objects. I want a connection with string theory, so I will mainly focus on compact objects that can be formed of moduli that are displaced after inflation from their late time minimum. And in this context, it is natural to think about oscillons. Oscillons are pseudo-solitons whose stability relies on attractive self-interactions, while the effects of gravity are negligible. In particular, the self-interactions, let's focus on a simple example. In this case, for instance, with the quartic self-interaction and the mass term, oscillons exist if G is less than 0, it's negative. And you can see that if you rescale the coordinates in this way, you write down the equation of motion, expand the field using this small parameter epsilon, and then solve the equation of motion order by order in the parameter epsilon. You will see that the dominant term is given basically by an oscillating cosine times a bell-shaped profile like in this figure. So this is basically going up and down, and then there are corrections. So these are non-topological pseudo-solitons, so there is no topological charge that stabilizes them, and they will eventually decay. And there is plenty of papers studying the stability of these objects, but they are very long-lived. I put here just a very old paper, one in the middle, and a very recent one, but you can find many more. And in this simple example that will be relevant for the rest of the talk, the mass of the soliton and the radius can be written in terms of the mass, the parameter epsilon, the coupling in this way. Okay, what are the conditions for the formation of these objects? First condition is that the quantum fluctuations have to grow, so you need some kind of resonance. And two examples that have completely different behavior are narrow parametric resonance, in which the growth of the fluctuations is very slow, as you can see, or tachyonic resonance, in which the growth is very large, very fast. And we will encounter both of these behaviors in the following. And so if the fluctuations grow, you end up with this kind of situation. You have very large fluctuations in the energy density of the universe. And of course, so if the interactions are repulsive, these fluctuations will just disperse very quickly and nothing else will happen. While if the interactions are attractive, they will clamp and compact objects will be formed. The second condition, as we have said, is that the interactions have to be attractive, and this translates in terms of the potential, it has to be shallower than quadratic. And this condition is met by the two models that we have studied in the first paper on this subject, namely KKLT and blow up. And you can see that on one side of the minimum, these potentials are shallower than quadratic. Okay, in all interesting cases, the dynamics becomes nonlinear, so one has to resort to lattice simulations. And in this case, we used lattice DESY, which is a code that evolves the Klein-Gordon equation on expanding background. And here you can recognize the different behaviors due to parametric narrow resonance in the case of KKLT, with a slow growth of the perturbations, and tachyonic resonance, in which, in the case of blow up, in which the dynamics is much more chaotic. Okay, please note that these compact objects, once they are formed, they can interact, they can collide, especially they are not spherically symmetric, and these are all sources of gravitational waves. So this is the spectrum of gravitational waves at the emission time that you will get. You see that here we have a peak around the mass of the field. In the case of blow up, we don't see a peak because for computational reasons, we didn't run the simulation for long enough. But if you wait for enough time, I mean, we would expect to see a peak also in this case. Is there a question? Chat.
Yeah, go ahead.
Okay. Okay. So if you redshift the spectra to today, you would see that this peak gives rise to a peak in the today's spectrum, which is around 10 to the minus 10. And this doesn't look extremely bad. You know, if you think that LIGO will put a bound which is around 10 to the minus 9 in terms of omega. But please note that this will be at rather different frequencies, around 10 to the 7, 10 to the 8 Hertz. Okay, so assuming oscillon production, this is the scaling of the frequency in general. It goes like the mass to the 5/6. And assuming oscillon production, one can explore various values for the mass of the moduli. In particular, one can, with 400 GeV, one is in the range of LISA. With 10 to 9 GeV, one is in the range of LIGO, and so on. And the dream goal would be to be able to read partially the spectrum of the moduli which are involved in this kind of non-perturbative dynamics from the spectrum of the gravitational waves. Now let me make a little detour and introduce a comparison with the electromagnetic spectrum. So we know that the electromagnetic spectrum spans many orders of magnitude in frequency. And it is also well known that different frequencies correspond to different physical phenomena. For instance, in terms of atomic and molecular transitions. So it's interesting to ask what can we learn at each different range in frequency from gravitational waves. And we already know with the currently operating or proposed detectors that each range in frequency corresponds to different physical phenomena. For instance, at the CMB scales, you probe inflation, and this is on the left of this plot. Then you have the PTA scales, so you have supermassive black hole mergers or cosmic strings. At LISA scales, you have other phenomena like galactic compact binaries, supermassive black hole mergers, phase transitions, and so on. And at LIGO scales, you still have black hole and neutron star binaries, phase transitions, and bursts, for instance. So but it's very natural to ask what would we learn at higher frequencies than those explored by LIGO. And it's particularly interesting because since we are talking about high frequencies, this will correspond to very short wavelength. So 1 gigahertz will correspond roughly to 1 centimeter of wavelength. So in principle, these detectors in this region of the frequency range will be small scale experiments, so will be cheap and easy to build. And this is an example. So for the details of the detector, I refer to this paper by Maxime Goryachev and Michel Tobar. And this is basically, you see less than 5 centimeter cube, and it's based on phonon trapping acoustic cavities technology. Okay, but on the other hand, these are quite difficult to, these frequency gravitational waves will be quite difficult to detect, because if you take, this is the relation between omega gravitational waves and the characteristic strain, which is what you would like to compare with the with of your detector. And you see that for a given value of omega, H goes down with the frequency. Okay, so if you are interested in the LIGO frequency range, omega equal to 10 to the minus 9 will correspond to a characteristic strain of 10 to the minus 24, roughly. But if you go with the same omega, you go to 10 to the 8 Hertz, this will correspond to 10 to the minus 30, which is quite a dramatic change. But not everything is lost. So let me remind you what is the story of gravitational waves. It's a story that shouldn't have been at all from the very start, right? Because Einstein predicted that gravitational waves will never be observed. And the technological gap 100 years ago in the LIGO frequency range was of about 16 orders of magnitude. I refer to this nice review about the history of gravitational wave detection to read about this. And even if you open the Bible of gravitation, which is Misner, Thorne, and Wheeler, you will learn that interferometers are of little experimental interest. Okay, so there is room, so technological progress plays a crucial role here. And this is why we organized recently a think tank workshop at ICTP, gathering experts and people interested in the subject, both from the theoretical and the experimental point of view, to discuss possible strategies and to push on this, to boost the interest on this topic. And we are going to produce proceedings that will appear soon. That summarizes the state of the art, and hopefully it will be a starting point to push on this subject. So here I took a preliminary plot about the sources that we are collecting in this, about some of the sources that we are collecting in this proceedings. So you see that here is the BBN bound, okay? And just below the BBN bound, a lot of sources are present. So the important thing will be to go with the sensitivity detectors below the BBN bound. Now take this with a grain of salt. We still have to double check all these curves, and we are not even sure that this is the best way to present them, because we are not presenting spectra, we are presenting like upper bounds for these sources. But the important point that I want to share with you is that if you take the most promising detector that was presented by Mike Ruiz at the workshop, and I refer to his talk for learning more about this, this is about 6 orders of magnitude away from the BBN bound. So it's not that bad, and I hope we will be able to keep working on this. And if you're interested, keep an eye on this. I think that this audience should be very interested in this topic, since it's a very nice experimental alternative to look into high frequency, high energy physics. Okay, let me go to back to the main theme of the talk. And so one of the obvious questions that one could ask when oscillons are produced is what is their fate? We have seen that they are in principle very long-lived, but can they collapse to black holes, for instance? And this is easy to see if we consider the simplified example that I showed you before. So take again the massive scalar field with the quartic interaction. We have seen that the mass of the soliton and the radius take this form. So it's easy to write the ratio between the Schwarzschild radius and the radius of the oscillon. That goes like m over m Planck squared. In the case of axion potentials, we can be even more explicit because we know that G takes this form. And in this case, basically you see that the ratio scales like f over m Planck squared. Okay, so when f is of order m Planck, the effects of gravity are not negligible. Now, in the case of moduli, the role of the axion decay constant is played by a parameter lambda and energy scale, which in the case, for instance, of KKLT is of order m Planck, 0.1 m Planck, while in the case of blow up is suppressed by the root of the volume. And when lambda is of order m Planck, gravity is not negligible for these objects. Before going on, let me say why this is interesting to start with. So one point is that gravity provides an additional attractive force. So one might ask, maybe consider taking into account gravity, it's easier to have stable solutions to form this kind of objects. And I will show you that this is exactly what happens. Second reason is that analytical estimates show that the spectrum of gravitational waves is proportional to the fourth power of the amplitude of the oscillon, or the amplitude of the field inside the oscillon. And again, I will show you that the effects of gravity is to enhance the amplitude of the field inside the oscillon. So this is again an effect that enhances the gravitational wave production. Then also the effects of gravity lead to a larger compactness of these objects. And the larger compactness means, as you can see from this plot that is taken from a paper by Thomas Helfer, Eugene Lim, Garcia, and Mustafa Amin, that larger compactness means large amplitude in the gravitational wave. And also you can form a black hole from oscillon collisions. And finally, you can have, indeed, as I was saying, you can have light primordial black holes that can be the initial conditions for Hawking genesis, and they would transform, they will give these compact objects a longer life. So these black holes could cluster. There could be more dynamics, and again, this would enhance the gravitational wave production. In the case, when you add gravity, these objects are called oscillatons. And the main point here is that you just need a free scalar field. You don't need any more potential which is shallower than quadratic. And it's easy to write down, to find the solution. You just assume spherical symmetry with the free scalar field. We can Fourier expand all the fields, and then it's just a matter of solving the Einstein plus Klein-Gordon equations. In order to do so, you impose some boundary conditions, in particular the regularity at the center of the solution and the asymptotic flatness, and then you can use a shooting method, which means that you fix the first coefficient of the field, of the scalar field. And then you tune the other coefficients of the expansion in such a way to satisfy the boundary conditions at infinity. In this way, you obtain a one parameter family of solution. Here I'm plotting just the profile for the scalar field. And just to give you, for different total masses of the oscillaton, and just to give you an idea of which kind of masses and radii we are talking about, these are the typical values. Okay, little m is the mass of the field. Okay, so the stability of these objects is very well studied in the free field case. The one parameter family of solution splits into two branches: a stable branch, which is this one, and if you perturb configurations on this branch, what happens is that they just go back to the stable branch. And a stable branch in which if you perturb configurations, they either migrate to the stable branch or collapse to a black hole. Now, the problem is that you cannot do this study in the interacting case in a similar way. You really need to resort to GR simulations. And that's why I will introduce this amazing tool, which is called the GRChombo. GRChombo is a code that has been developed in the UK, starting from about 10 years ago by a group of more than 10 people. These are just the currently active developers, to which you have to add many other people. And it's an amazing tool because it's an ongoing project. So basically, people are working to enrich this code with new tools every day, and so the code never ages, basically. And it combines numerical GR with the adaptive mesh refinement. And towards AMR, just means that the code monitor a chosen quantity at each time step and insert higher resolution subregions where this quantity exceeds a pre-specified threshold. This could be, for instance, the energy density. And the refinement means that each cell is refined into 2 to the cube cells. And this is what you will see in the simulation grid. You see that whenever it is needed, the code adds more refinement levels in the grid. Now, for us, the tricky part is the initial conditions, because to start the simulation, you need to provide all the fields on a time slice that satisfy the Hamiltonian momentum constraint. And these are quite difficult to be solved. But we use a trick and we exploit the fact that we know the solution for the free field case. So if you think for a moment about it, rho contains the kinetic terms plus the gradients plus the potential terms. So if you choose a moment of time symmetry in which phi is equal to 0 everywhere, basically you are killing the gradients term and the potential term, and the solution is the same as in the free field case. And also you're killing the gradients here, so this is identically satisfied if the extrinsic curvature k is equal to 0. So we use this trick, and basically we use the initial conditions taken from the free field case to start the simulations. And in this paper we consider various potentials beyond KKLT. In particular, E models, which are Starobinsky or fiber inflation-like potentials, which are asymmetric around the minimum, and the T models, which are symmetric around the minimum. Okay, so this is the parameter space that we explored. You see, for each model, we vary the parameters, and then we vary the total mass of the initial configuration. We are assuming spherical symmetry here. And we study the fate of these compact objects, both in the case in which gravity is switched off and in the case in which gravity is switched on. You immediately see in the free field case, we have seen that if we don't have attractive interactions, there is no pseudo-stable compact objects. Instead, in fact, you have dispersal in all the cases, while once you add the gravity, you have metastable objects. In the case of KKLT, we just get metastable objects, but you see that the amplitude of the field is larger in the case with gravity. This is what I was saying before. And remember that omega gravitational waves is proportional to the fourth power of the amplitude of the field. This is the field at the center of the oscillaton. In the case of T models, you see there are cases in which either with gravity or without gravity, you only have metastable solutions. And there are cases in which you have metastable solutions without gravity, but once you switch on gravity, you get a collapse to a black hole. And this is the typical plot for that you find in a collapse to a black hole. Chi is basically the inverse of the determinant of the spatial metric to some power. So when it goes to zero, basically means that we are hitting a singularity. And E-models are even more interesting because there are cases in which you have dispersion without gravity, while once you switch on gravity, you either have metastable compact objects or collapse to a black hole. So this is an example. This is the field at the center of the oscillaton. You see that without gravity, the blue curve, this is the field at the center, it's just dispersing. While with gravity, it's growing and then it collapses at some point. So it's a dramatic change. And this is what you will see in a simulation. This is a slice. So you see the field plotted here. And it's going very slow. But you will see that at some point it's just disappears because it collapses and it disappears behind the horizon. Wow, this is very slow. Okay, it's not working, sorry. Okay, let me say that we are extending these results to other kind of models. In particular, I received this plot yesterday by Zainab Nazari, who is a visiting student at CTP. We are exploring other kind of potentials. But even more interesting, we are extending this work in many other ways. So first of all, one could ask, okay, but in string theory, you typically have, at the very least, you have also the axion which is associated with the modulus. So we are trying to study the complex case. Now, the problem is that in field theory, the solutions in case, if there is a U1 symmetry in the complex field, are very well known. They are cuboids or boson stars. Depending on whether you're taking into account gravity. But the problem is that in string theory, we don't have this kind of U1 symmetry. And getting the initial conditions without this U1 symmetry is very challenging. So we are struggling with that at the moment. And then, of course, here I've talked about the fate of this oscillatons. We have, I mean, these simulations, we have just taken the oscillaton, put it in the center of the box and evolved it. We are trying to do it from the very beginning to study the preheating in these models. And also recently there have been papers in which it has been proposed that oscillons could compose part of the dark matter. So it might be very interesting to get a waveform for the collapse of these oscillons when they are non-spherically symmetric. This could even be immediately compared with the LIGO data to see if there is there are signals of this kind. But again, for all these problems, the trickiest point is getting the initial conditions. So we are currently struggling with that. Okay, so let me go to the conclusions. Gravitational waves can be seen as a very precious new tool to explore the early universe. And I've showed you, hopefully, that we have new tools also to better understand some models and interesting regimes. And but I would say that in order to exploit this at best, we need more work on high frequency gravitational wave detection. I hope that will be in the future. Also, let me, since I have 1 minute more, let me also say that this is gravitational waves are not it's not the only tool to explore the early universe. One can take a more theoretical perspective on that and study things like the quantum cosmology, so orthologging wave function, tunneling wave function, how the universe is born, etc., etc. And in this context, just keep an eye on a paper that is going to come very shortly in collaboration with Fernando, Shanta, and Sebastian, who is a postdoc in Madrid at the moment, in which we revisit the question whether the universe is bound to be open as a consequence of the string landscape. This will come very soon. Okay, I'm done.
Good. Okay. Thank you, Francesco. Thank you for keeping for the time and a very nice talk also. So questions, I see Kumrun is raising his hand. Kumrun?
No, this was from the previous one, I think.
Oh, okay.
There's a misunderstanding. There's no question.
No question. Anybody else a question?
David, maybe.
I don't see it.
Hi. Thanks for the nice talk. Yeah, I was just wondering about the oscillons. So the main feature of the gravitational wave would be that the frequency is given by the mass. So is this a monochromatic gravitational wave, or is the range of frequency larger actually?
There is a peak, but it's not monochromatic. Yeah. But the interesting thing is what happens in case of complex fields. No, if you have like a modulus and then an axion, you have two scales in principle, and they are also coupled to the kinetic terms, say. So it's interesting to ask what kind of phenomenological features would have the gravitational wave spectrum in that case. I'm not sure.
Okay, thank you.
Yeah. Okay, good. James, you have a Jim question?
Hi, Francesco. Nice talk.
Hi.
Yeah, simple question. Really nice talk. I like these oscillons a lot. As you know, sometimes funny things can happen when you crank up the number of fields to dozens or hundreds like we expect. I know that these sorts of numerical analyses can run into issues at large n, but is there some sort of expectation that oscillon formation and dynamics might be kind of general or tractable or interesting at large n, or is not much known yet?
Yeah, I'm not completely sure, but we were discussing about this with Alexander, whether it might be interesting to try and extract, using statistical methods to extract some kind of prediction in that case. I think, I mean, simulating such scenarios is impossible. I mean, at least at the, given the current technology, but maybe using some statistical methods that might be possible in the future, yeah.
Because the simulations are already pretty intense at a few fields in terms of runtime, right?
Yes, very intense, yeah.
Okay, thanks.
Yeah, I think that in this case you have, so for the simulations that I've shown, you have like 2 million points for each level. And for the cases in which you have black hole formation, we went to 7 levels. So they're pretty intense.
Right, and so getting up to dozens of fields is just going to be
no.
That is
so
you really want to do it via other means, these statistical means that you mentioned.
Yeah.
Okay, thank you.
Very good. So I can add some comment also. Is just a point about this high frequency gravitational waves that I think is very important to emphasize, is that beyond the LIGO regime, there are no other candidates from astrophysical events. So everything that you can study beyond the LIGO regime has to be cosmological. So either it can be any of these oscillons or preheating or something, or phase transition. But the good thing is that essentially exploring high frequency gravitational waves will open up a lot of different ways to observe some cosmological features that we cannot observe from
Yeah,
otherwise.
actually, there are very few sources that might be of astrophysical origin, like super radiance or exotic compact objects like in spirals. Now, if they are a bit lighter than, say, neutron stars or black holes seen at LIGO, they may fall in the high frequency range, but not very much. Mainly, it is just cosmological sources. Yeah.
Very good. Okay, well, thank you very much, Francesco. So let's move to the next